Okay, let's go ahead and get started with section 1.3. In this section, we're going to continue to use the simulation models that we've been working with, but now we're going to look at various discrimination cases. Okay, let's go ahead and get started. The case study that we're going to look at here is from an article in the Boston College Law Review. And in particular, in this article, they presented a variety of cases in which statistics were used in the courts. For example, there is a situation in which Mexican Americans had been underrepresented in the selection of grand juries. This took place in a county in Texas. A second case, titled Hazelwood School District versus the United States, was centered around the hiring practices of minority teachers in that particular school district in Missouri. The case that we're going to look at is titled Greenholtz versus Nebraska Penal and Correctional Complex. We're going to look at this case because the actual data were provided in that article mentioned above. Now, the plaintiffs in this case argued that Native Americans and Mexican Americans were not paroled at rates similar to other races. So let's go ahead and look at the data that was presented. In this table, we have a breakdown of 4 different ethnicities: white, black, Native American, and Mexican American. The middle portion of this table identifies those that were eligible for parole at the beginning of the study. Here there were 902 individuals that were eligible for parole, and the breakdown of these numbers for each of the races is provided in the middle. On the right-hand side, we have the inmates that were paroled over the course of the study. So of the 902 that were eligible for parole, 535 actually received parole. What the courts decided was that the percentage breakdown for those that were eligible for parole were close enough to the percentage breakdown for those that received parole. For example, they deemed that this 26.1%, okay, where did the 26.1% come from? That's simply 235 divided by 902. So this 26.1% is the interpretation of that value is 26% of the individuals that were eligible for parole were black. And they compared that to the corresponding percentage over here. The corresponding percentage over here is determined using 148 divided by 535, which is 27.7%. So they said, the courts said, that this 26.1%, which is the percentage of blacks eligible for parole, were close enough to the 27.7%, which is the proportion of blacks that received parole. Now, they didn't do this just for blacks, but they did this for all of the races. And they deemed these percentages matched the percentages eligible for parole close enough, and decided that there was not discrimination taking place. Now, a simulation model can be a little bit more careful than simply deciding that a certain set of percentages are close enough to another set of percentages. In particular, what we're going to do is identify whether or not the number that were paroled were close enough to what I would expect under a no discrimination situation, or under a all things fair situation. So we can use our model to determine what these numbers would look like under a fair situation. And that's what we're going to do next. Okay, as I said, the statistical approach is going to be to compare the number that received parole against the number we'd expect to receive parole under a situation of no discrimination. And our initial analysis here is going to focus on Native Americans. Okay, the setup of the simulation study is going to be as follows. The number of trials is going to be identified by the number paroled. In this particular situation, there were 535 individuals that were paroled. So this is going to be identified as our sample size, simply the number of trials. The other important component that we need to identify is that percentage. And this percentage for this simulation model is going to be that 6.5%. Now, what does that 6.5% represent again? That's the chance of obtaining parole for Native Americans under an all things fair or no discrimination situation. Let's go back up and look at our table and make sure we understand where these numbers are coming from. The 6.5% again is the percentage of Native Americans that were eligible for parole. And under an all things fair situation, I would expect that the percentage over here that received parole would also be 6.5%. So we would simply, to identify the expected number, we would take that 6.5% and multiply it by 535. We're going to compare that number against the number that we actually received parole, which is 24. So again, to compute the expected number of Native Americans to be paroled under a no discrimination situation, we would simply multiply the sample size of 535 by that percentage of 6.5%. And when we do that, we get an expected value of 34.8. That expected value is what we're going to use to compare our observed outcome against. In particular, there was a total of 24 Native Americans that were paroled. The goal of the simulation then is to determine how likely or unlikely is it that we'd observe 24 under a situation of no discrimination. In particular, our specific question of interest is the following. Is there enough evidence to suggest that too few Native Americans were paroled against a no discrimination situation? The following schematic will help identify the setup of our simulation model, and we'll be seeing these as we move forward into our examples. Some of the various values that we care about here on this schematic are the following. We care about the lowest possible value. The lowest possible value on this number line would be 0. In other words, we could have seen no Native Americans paroled, and in that situation, we would identify that discrimination was taking place. The highest possible value on this number line would be 535. We could have seen 535 individuals that were Native American in which all of those received parole. The label is going to simply be the number of Native Americans, and this is the quantity of interest in our investigation. The center of the pyramid is identified by the expected value that we computed above, and this is just the expected number of Native Americans paroled under a fair situation or under a no discrimination situation. Again, the simulation model is going to be built under a situation of no discrimination. The study outcome, we'll identify that in the number line up above here, is going to be 24. And this is simply the number of Native Americans that were paroled. And our goal here is to identify whether or not 24 is an unusual outcome against a situation of no discrimination. What side of the distribution do I care about? Well, I care about the left side because I care whether or not too few Native Americans were being paroled. So the left side is going to identify too few Native Americans. If we use the 2AFC app, it would be set up in the following way. My first outcome that I care about is Native American. The probability that is associated with that group is going to be that 0.065 or 6.5%. Now I have to identify an outcome, the other outcome. Okay? For a 2AFC situation, there has to be two choices. So here I'm identifying, I really only care about the Native Americans, but I need to identify the other outcome as, say, non-Native American or just other. And the percentage there is going to be 0.935. The other category includes the whites, the blacks, and the Mexican Americans in this situation. As I said above, the sample size is 535. And this is the number of trials, or the number of parolees that we had in this study. Setting this up in this way and clicking Run Simulation will provide one set of outcomes, right? It'll provide a tally for what the numbers would look like if there was no discrimination taking place. again, because I'm specifying the 6.5% here for Native American, the simulation study represents the fair situation or no discrimination. Okay, and here's a set of 4 of those outcomes here. In particular, on the first run, I got 26 Native Americans that were paroled, 509 others that were paroled. Okay, so that total has to add up to that 535. The next simulated outcome was 38. The third one was 35. And 35 is what I would expect. We computed that value up above to be about 34.8. So that's right on the expected value there. And then a fourth simulated outcome. And we could keep obtaining those simulated outcomes. Now, this 26 quantity, the 38 quantity, the 35 quantity, the 39 quantity, we actually have a name for those quantities, and that's called a statistic. A statistic is just simply a summary measurement that we've computed from data. And in fact, this is where statistics gets their name. We want to study these summary measurements over these repeated outcomes here. I went ahead and did 6 additional to obtain a total of 10 repeated outcomes. And I included those there in my top graph. So here's what my outcomes look like. Okay, the first outcome I had was 26. That's being plotted here. Second outcome was 38, which is here. I got a 35, and then I got a 39. So this is giving us an idea of what the repeated outcomes would look like under a fair situation. And in particular, I did 10 repeated simulations here to obtain my graph. I also have a graph from another person, okay, and a third person, and also a fourth person. And our first set of questions here then is what similarities exist in these 4 plots? Okay, so when we look at these 4 plots, what similarities exist in those plots? Well, things that I see are the center of each is around 35 or so. Okay. It looks like the center of the fourth plot might be more around 36 or 37. Okay, and the center of the second plot might be closer to 34 or maybe even 33. But generally speaking, the center of each of these simulated outcomes is around 35. This should be the case because 35 is the expected outcome. So even though each of us are going to see different outcomes, we all should be centered around 35 in a sense. Now, what differences exist? Well, the differences tend to be more on the edges. Okay, so on my outcome, the lowest that I seen was 26. The second person here, the lowest they saw was 27. Or even on the upper side, my highest outcome was 46. But the second person's highest outcome was 42. Person number 3 kind of had points all over the place. They went clear down to 21 and clear up to 48. Okay, so differences tend to exist on the edges. So on the edges of these outcomes, how about we say differences tend to exist on the edges of the outcomes. Now, this is a concern because we're going to use these simulated outcomes to identify, okay, the purpose here is to identify the likely outcomes from the unlikely outcomes. And in particular, that division line is going to be on the edges of these distributions. Okay, so that's problematic in that I'm trying to figure out where that line is between likely and unlikely outcomes, but I don't have very many outcomes out here on the edge. How about question 3? It appears that the 10 repeated outcomes for these individuals tend to vary somewhat. Why is this a concern when trying to determine whether or not 24 is an unusual outcome? Well, I think we just answered that, right? Okay. The goal here is to, let's go ahead and bring that up a little bit. The goal is to determine whether or not 24 is an outlier or unusual. We need more data on the edge of these plots to determine this more accurately. So what do I mean by this? Again, trying to decide whether or not 24 is an unusual outcome. See if I can get all this on one page. All right. Certainly what would help is obtaining more repeated outcomes instead of just 10 as I have here. Okay. I could, instead of just getting 10 of these, get 100 of these. Or if I wanted, I could get 200 of these. Okay. Now that's not going to be very easily with the 2AFC app that I have provided up to this point. Well, it could be done. And certainly when graphs are based on more dots, like the one presented here with 100 dots, or I got a couple of graphs here presented with 250 dots. So graph number 2 is based on 250 dots. Graph number 3 is also based on 250 simulated outcomes. We can tend to see, or what we do see, is that these edges are a little bit more clearly defined. Certainly when using 250 repeated simulations, these edges are more clearly defined than if we had just used 10, as I was shown up above. We really start to better understand what likely or unlikely outcomes are, or in particular where that division line is when we base our plots on many, many repeated simulations. So just some comments about the graphs that we're seeing here. All of these graphs are centered around our expected value of 35. All graphs peak at about 35, and the edge on the lower end is around 21 or 22. So again, the edge here is right around 21 or 22. Likewise on a separate graph based on 250 repeated simulations. Also on the high side, it looks like the edge is right around 49 or 50, and that is true on both of these graphs as well. Graph number 2 and number 3 are similar because so many repeated outcomes were obtained for each of those. So certainly the differences that I anticipate between one person's simulation and another person's simulation diminishes when each is based on many, many repeated outcomes. So the influence of atypical points or certain observations is going to be less when I'm basing it on many, many repeated simulations. Now this is seen here as well with a sequence of 4 graphs that have been presented. Let's see if I can zoom out a little bit and get all 4 of these graphs on the screen at once. There we go. From these 4 graphs, okay, this first graph is just based on 10 outcomes. The next on 100. Graph C is based on 1,000. And graph D is based on 10,000 outcomes. Okay, so I'm using a computer, okay, to generate these 100, 1,000, and 10,000 outcomes. You can use the 2AFC app quite easily to just get outcomes, 10 outcomes like I've discussed above. Now, what similarities exist in these 4 graphs? Well, again, all 4 tend to have the same center point. Okay, so all 4 graphs tend to be centered around 35, or the expected value. Okay. Now, as we've been talking about, it's certainly going to be easier, okay, to identify what an unusual outcome is based in graph D than graph A up here, because graph A doesn't have very many observations to work off of. So when I don't have very many observations, say 10 repeated outcomes, it's hard to determine where that lower endpoint is or where that upper endpoint is. But when we base it on 10,000 outcomes, I have a really good idea of what that pattern's going to look like. Not only in the middle, but I have a good idea of what that pattern looks like over here on the left-hand side and also the right-hand side. So why is it easier to determine unusual in a graph with many, many more repeated outcomes? And the reason, or the answer to that, is with so many repeated outcomes, the edges, have, well, the notion of where likely and unlikely outcomes are is better understood. Again, just the quantity of observations out on the edges helps me do that. Let's go ahead and consider the third question here. What would you consider an unusual outcome to be in graph A? So let's go back up and look at graph A here. Again, zoom out a little bit, maybe to see all of these on the same screen. In graph A, it looks like the lowest outcome that I received was about a 28 or maybe 27 or so. So in graph A, I would say that 27 is kind of the point where I start to not see data points anymore. But however, that was only based on 10 observations. When I base that graph on 10,000 observations, we can see that 28 and 27 actually occurs somewhat frequently. Certainly more frequently than what I would say out here at 23 or 24 or 25. So what is a unusual outcome in graph A? Well, what did we say there? Anything less than, so anything less than maybe 27 or 28 in graph A. Okay, if we go down to graph, say C, okay, in graph C, where are we at? About 24, 25, 23, somewhere in there. Graph C, you can actually see these are somewhat more common than these down here. All right, so there's kind of, seems like there's kind of a split here between this here, which is at about 24 it looks like, and then down from 23, 22 and below. So if I were to use graph C, okay, in graph C, it looks like unlikely is anything below 24 or maybe 25 or so. All right, now we haven't been very careful about what I mean by unlikely outcomes. Okay, so maybe you believe that unlikely outcomes are those way down here. We'll talk a little bit more about that in a minute. So I haven't been real careful about what I mean by likely or unlikely outcomes. Okay, a little bit about how do I get these simulation models with many, many repeated outcomes. The 2AFC app that I've been working with and shown you, up to this point, you're only able to get a single simulated outcome each instant. Okay, so I'm going to show you one more app, and this one is called the Reference Distribution app. The link for that is provided here, and I will provide it on the course website as well. Now, how do we use that app? All right, we need to identify the probability of success in that app. Okay, and what we mean by a success here, okay, that word success is just a generic term for one of the two outcomes. In this particular situation, a success would be when a Native American is paroled. And again, the percentage for that under a no discrimination situation is that 6.5%. So that's going to be the value for the probability of success in the reference distribution app. The reference distribution app also needs to know the sample size. The sample size, as we've said here in this example, is 535. One thing that you do not need in the reference distribution app is identification of the other outcome. Okay, so that's not needed in the reference distribution app here. It was in the app that we have been using, okay, but we don't need that over on the left-hand side. The number of samples here, we need to be careful with this, but the number of samples is actually how many repeated simulation outcomes do you want. Okay, so that's what goes in this box right here. All right, so just some comments about using the reference distribution app, and I'll show you in its use here in a minute. The probability of success, which they denote by pi, not to be confused with 3.14. Okay, so we use pi, as denoted here, to identify the probability of a success, or the probability of an outcome of interest. Okay, and that quantity is actually referred to as a parameter. We'll talk more about that as we move forward in the next chapter, but that value there is called a parameter. That 6.5% is what we call a parameter. And essentially what that does is just indicates how far up the number line our pyramid sits. So this pyramid sits 6.5% of the way up the number line. The sample size, denoted here by n, is 535. The sample size, okay, is the maximum value on the number line. So if we're thinking about the schematic that we presented above, the maximum value on the number line was 535, and the pyramid sat 6.5 percentage points above the bottom. And that's the two quantities here that this reference distribution app needs. And in fact, that's the only two quantities we need to identify where that reference distribution is going to be placed, is the percentage and also the sample size. The number of samples, as I said a moment ago, determines how many repeated outcomes are desired. Okay. Other things, well, let's go ahead and go to that app. So let's go ahead and take that link there and go out to that app, and that's what we have here. So this is what this looks like out on the website, and this is developed by Alan Rossman and Beth Chance. They have a whole set of apps for simulation-based work, and that's what we're using here. As I've said, the probability of success is going to be that 0.065, so that goes in this box. The sample size here is going to be 535, and that goes in this box. Now the number of samples, we can specify however many we want. So if I go ahead and put 1 in here, that's actually going to run the simulation once. Okay, so let's go ahead and some of these other things that are somewhat distracting. The animate button, I'm going to turn that off, and then I'm going to hide the spinners as well. So I'm going to select hide spinners here, and that'll just make this app just a little less distracting. Now if we say draw samples, okay, so I drew my first sample here, and it looks like the value being plotted here is automatically being plotted on the dot plot. So my first one was actually at about, what is that, 49 or so? Okay, which is a little bit high from what I would expect. Remember, what I'd expect is values right around 35. So this went ahead and ran one instance of the simulation. Okay, so that is equivalent, what we've done so far is equivalent to what this 2AFC app was doing before. Okay, so again, that's just one situation or one run of what we did here. Now if we want a second run, I just simply need to say draw samples again. And the second sample was down here at about, what is that, 27 or so. Okay, so I can just simply select draw samples. So if I do 10 of those, for example, okay, there's 10 of them. Okay, so again, this is 10 simulated outcomes for the Native Americans under a situation of no discrimination. And these plots here, or this plot here, okay, looks very similar to those that I presented earlier. In the graphs that I presented earlier, I had 10 repeated outcomes. Okay, and this one actually goes down to about 24 and up to about 50. Now the nice thing about the reference distribution app is that I can real quickly get many more samples. So if I say number of samples is 90, that's just going to add to the 10 that I already have. So that's going to give me a total of 100 simulated outcomes. Again, I'm getting more and more dots centered around the 35. I'm getting more dots even on the edges, which helps me identify what unusual observations look like. So this graph that we have right here is based on 100 total repeated outcomes. Okay, so if I wanted 250 total repeated outcomes, well, I already have 100. So if I get another 150, I can ask for that. Okay, and again, I'm getting so now I'm up to 250 simulation outcomes. I'm starting to get a nice peak here at 35, and then it's going down on each side from there. Now I can get many thousands of repeated outcomes if I wanted. So here, it's going to take a little bit for the computer to do it, but here I have 10,000 repeated outcomes now. And this is the graph that I was looking up at above. Based on 10,000 repeated outcomes, I have a really good idea of what's going on the edges of this graph. And again, the edges are most important because I'm trying to separate likely from unlikely outcomes. So the reference distribution app is quite convenient when you want to get lots and lots of samples. And we'll be using this app throughout the rest of this chapter and even into the next chapter that we are looking at. Okay, so let's talk a little bit about the outlier rule. The overarching goal here in this investigation, as I've stated, is to determine how likely or unlikely it is to see 24 Native Americans paroled under the situation of no discrimination. Okay, now this app makes determining that value quite easy. Okay, so down on the lower, if I go back to the app a minute, in the lower left-hand corner, there's a box in which you can enter a value and it'll calculate how many values are as extreme as that value. So down here in the lower left-hand corner, okay, I simply say as extreme as, and I want to move this to the left side of the distribution because again I care about too few Native Americans. So I want to be on the left side here. So that has to be switched. Sometimes we care about too many. Okay, for example, in the staring example, I cared about the right-hand side of the distribution, so I would leave it like this. But I care about the left-hand side, so I want to change this to the lower than. And then I simply put in, say, 24. Okay, or I can put in whatever value I want. I can put 20 in here. And what's going to happen when I put that 20 in that box, or that 24 in that box? Well, what ends up happening there is it actually counts the number of dots that are at that value or below that value. And that's going to give us an indication of how unlikely that is. So in particular, based on these 10,000 observations, I had 298 situations where I had 24 or less Native Americans. Okay. I had 298 instances in which I had 24 or less Native Americans being paroled. Okay, so that happens about 3% of the time. Okay, so one more time, what does that 3% represent? 3% of the time, I would expect to see 24 or less Native Americans being paroled. Okay? And that 3% is being computed under what it should look like if things were fair. So, what that means is it's not very likely that I'm going to see 24 or fewer Native Americans being selected for parole. Okay? That's only happening 3% of the time under a all things fair or no discrimination situation. But, okay. So is that unusual? Or what do we need some sort of kind of a target to base our decision making off of. And that's what we're going to talk about next here, is the outlier rule. So what is the outlier rule? The outlier rule determines the location on the distribution for which one begins to believe that observations are unlikely. The widely accepted rule is to use 5% of the distribution. Okay, so let's talk about that a little bit before we... A statistician is going to argue that the determination of what constitutes an outlier should not be adversely affected by the number of repeated outcomes. Okay, so what we mean by that is that if somebody bases a graph off of 1,000 repeated outcomes, the determination of an outlier, okay, should not vary much from somebody else who bases a graph on 2,000 repeated outcomes, or even somebody else who might base their graph on 500 repeated outcomes. So the number of repeated outcomes that one uses in the simulation should not adversely affect what value we decide for unlikely versus for unlikely versus likely outcomes. Using the 5% rule helps regard against that effect, okay, and helps minimize the effect that different simulations might produce slightly different pictures. As I've stated, the purpose of the outlier rule is to separate the likely from the unlikely observations. Now, the outlier rule is always based off of a reference distribution. It's always based off these pyramids that we're building. So certainly to understand the impact of using the outlier rule, you have to carefully consider the situation in which the reference distribution represents. So we really need to understand what that reference distribution represents. In this case, it's the situation of no discrimination. Okay, so let's go ahead and try to apply the outlier rule to the given situation that we have here. So finding that cutoff value. Okay. So again, I need to identify the bottom 5% of the distribution. And again, I'm using the bottom portion of the distribution in this example because I'm interested in whether or not we have too few Native Americans being paroled. So I'm going to go ahead and move or specify a value of 25 here in that box on the reference distribution app. So let's suppose that, or let's identify the cutoff value to be 25. Okay, at 25, what I had was 454 observations that were at 25 or less out of the 10,000 that I obtained. Okay, so I'm basing this on 10,000 repeated outcomes. So I have, again, a pretty good idea of what's going on. When I lay down the value, or if I say 25 is my cutoff value, I'm going to have 4.54% of the observations below that. So again, the 454 divided by the 10,000, or 4.5%. So that looks like a pretty good value for when I start to believe, or excuse me, that looks like a pretty good value for determining what constitutes a likely value from an unlikely value. Again, the red indicating the unlikely values, the black indicating likely values. If I were to slide that cutoff up just a little bit, so let's try to move that up to 26 instead of 25, what is going to happen? So now I've, in the box, in the as extreme as or less than or equal to box up here, I've specified 26. So I move that dividing line up just a little bit. When I move that dividing line up a little bit, I'm going to gain more observations to the left. Okay, so before, when I was using 25, I had 454 observations that were identified in the red. But if I move this up to 25, I'm going to have slightly more in the red area. And when I do that, it looks like I have a total of 667. Okay, 667 divided by the 10,000 is about 6.7%, or 6.8%. Actually 6.7%, isn't it? I have a typo over here, which I'll just go ahead and fix that right now. That should be 6.7%. Now this 6.7% is slightly above the goal of having a 5%. Okay, so again, the widely accepted rule there is the 5% of the distribution. So this indicates that 26 might be a little bit too high in determining what likely or unlikely observations are. And in fact, 25 seems to be the magical number for the cutoff. Okay, because at 25, I have about 4.5 percentage points to the left of that. So for this particular investigation, I'm going to say that values 25 or below would indicate unlikely outcomes. 26 and above are going to indicate likely outcomes. Okay, does that make sense? All right. There is different language that gets used here. Okay, so I've identified this as the outlier rule. And some people identify this 4.5% that I was talking about as the error rate. Okay, so let's talk a little bit about that. I've referred to the 5% rule as the outlier rule. And again, this is the value that separates likely from unlikely observations. Others refer to the 5% value as an error rate. So why do they call it an error rate? Okay, so let's talk a little bit about that. In using the outlier rule, one decides that a value of 25 or less, okay, so that's what we were saying up above, 25 or less, is statistically unusual. Okay, and that's going to lead to suggesting that possible discrimination is taking place. Okay, so anything less than that 25 is going to suggest too few Native Americans being paroled, which is going to suggest possible discrimination by the state of Nebraska. However, you must acknowledge that it's possible, okay, it's possible to get less than 25 under a fair situation. That's the situation that we're modeling here, is a fair situation or a no discrimination situation. So if I say that 25 or anything less than 25 is potential discrimination, I'm going to be making a mistake here, or I'm going to be making an error. And in fact, I'm going to be making an error about 4.5% of the time. Right? Because anything less than 25, I'm going to deem as unusual, which is going to suggest possible discrimination by the state of Nebraska. But it's possible, and in fact about 4.5% of the time, I'm going to get a value of 25 or less under a fair situation or under a no discrimination situation. So the amount of error that I could be making in my decision is at most 4.5%. Okay, so some people refer to that 4.5% as the error rate. Okay. And now I hope you understand where that's coming from. So let's go ahead and just recap what we've learned from this example. The question of interest is there enough evidence to suggest that too few Native Americans were paroled against the all things fair or no discrimination situation? And what did we determine there? Well, we determined that yes, statistically speaking, 24 would be considered an outlier against a situation of no discrimination. Okay, we laid down our outlier rule at 25 or less that we've specified up above. The study outcome is at 24. That's below, okay, the outlier rule. That's suggesting that too few Native Americans were being paroled here. Okay, too few Native Americans were being paroled. So there is at least some statistical evidence to suggest that discrimination was taking place, or at least possible discrimination was taking place. Now I will admit, or we should admit, that this 24 value is very close to that outlier rule here. Okay, it would be much worse, right, if there was only, say, 17 Native Americans that were paroled. But this value of 24 is pretty close to that cutoff value there. But strictly speaking, from a statistical perspective, 24 is an unusual outcome against the situation of no discrimination. And if we want to back that up with some percentages, if we want to be more careful about that or more explicit, in a no discrimination situation, seeing 24 or less happens about 3% of the time. Okay? Thus, seeing only 24 in our study outcome is an unlikely outcome, right? That 24 is an unlikely outcome. Certainly happening less than 5% of the time, and that 5% of the time is kind of our golden rule here. Okay, in the next section then, we'll go ahead and do several more examples where we can just quickly apply the outlier rule to a variety of examples. We'll use the reference distribution app, which allows us to do that pretty quickly. Okay, until next time then, we'll see you later.